Hello and welcome to the second Pixinsight tutorial for SAS members. In this tutorial we're going to continue with the linear processing of the integrated image created in the first tutorial. The processes that we're going to describe are cropping using dynamic crop, background extraction using dynamic background extraction, and or automatic background extraction, and then high frequency noise reduction with multiscale linear transform. Dynamic crop must be used to maintain the astrometric solution that will prove useful in future processes. The process can be found under Process, Geometry, Dynamic Crop. The process is dynamic, meaning it is an interactive process. This process enables the removal of edges where image integration can cause uneven overlap between your subframes after star alignment. It can also deal with misaligned filter sets. The process must be performed before background modelization because the uneven illumination of the edges can cause issues. There is also a useful method of applying the same crop to multiple images, as in an LRGB filter set or a narrowband filter set. Or if you're using a one-shot color camera, you may have different exposure times if you're doing a high dynamic range picture. The process is easy to use if it's correctly applied. In this video, dynamic crop will be demonstrated. To begin the process, go to Process, Geometry, Dynamic Crop. This set of the Sculptor Galaxy, we've got 3 filters, and the first thing we're going to do is examine each of the integrated images to see where the edges are. To do this, we apply a screen transfer function and then zoom in to the edges of the image. On this first filter, you can see there aren't really any discernible edges to this image. Have a look at all 4 corners. You can see on the blue integration image there are discernible overlap edges, and these will need to be cropped away. Again, have a look at all 4 corners to see the extent of the overlap. Finally, we'll have a look at the luminance image. Again, you can see, may not come up too well, but there you can see quite a discernible overlap and actually a missing piece where there is no data. So the next step is to choose which image you're going to do the crop to. In this case, I'm going to use the LUM image. Hit the reset button in the bottom right hand corner and you'll see there's now a box drawn onto the image. You grab the handles and move them in to take away the edges. You can of course zoom in if the edges aren't particularly clear. So there we have the crop in place. Now then, we don't immediately execute it. What we do is take the blue triangle in the bottom left and we drag it to a clear area of the workspace. This gives us a new instance of the dynamic crop. So now we execute with the green tick. This crops the image, and then we cancel with the red cross. That image is now cropped. We now open the next image, and then we double click on the process. And what this does is execute the process with exactly the same crop as the previous image. Green tick, cancel with the red cross. That image is now complete. We then move on to the final image and repeat the process once more. The next process that we're going to look at is background extraction. This removes gradients from the integrated image. Gradients can be caused by light pollution, the moon, and certain issues with the optical system. There are two options under the background extraction process window: automatic background extraction and dynamic background extraction. Automatic background extraction is simple to use, and it's fine for galaxies and structures that are well defined against the background. Dynamic background extraction is best for large structures and nebula that fill a large proportion of the frame, as it allows user-defined points and more control. With DBE, it's very important to select the reference points carefully to avoid destroying legitimate signal or including stars. This is an important step. It gives a huge improvement to the image, and it requires time to execute so that you can get the best results. In terms of the removal of gradients, there are two options. You can use division and you can use subtraction to remove the gradients listed above. There is a process which is known as double DBE, where first the division is used, followed by subtraction. This is useful where flats are not available or acquisition takes place under a bright moon. Double DBE works well on narrowband images shot under a full moon. I've personally used this to good effect. I will now demonstrate dynamic background extraction on this image of the Sculptor galaxy. We start by going to Process, Background Modelization, Dynamic Background Extraction. Here you can see the process window. As it's a dynamic process, we need to activate it using the reset button in the bottom right corner. You'll now see a grey cross across the screen, the image, and that means the process is active. The first thing we're going to do is to look at the image correction, and in this case we're going to use subtraction. That's the most used case. We're not going to tick normalize or discard background model. Leave all of those three unchecked. That will enable us to see the background model and to create a new image to compare. The next step is to look at the sample generation. These are the samples that will look for the gradients. You don't need a large number of sample points. Anywhere between 10 and 30 is acceptable. If you're starting to get into the hundreds, then it's far too many. Gradients are large, and therefore you don't need a lot of sample points to pick them up. So generate using the default samples, and you can see we've generated 11 points. In the center of the process screen, you'll now see a pixelated square, and this shows you the pixels that have been sampled by that particular sample point, and that sample point is shown on the left hand edge of the screen in green. What we can now do is look to cycle through the various points to see the quality. If you get a star, this will appear as a black circle within the screen, and this point should be discarded using the red cross. Sampling through the different points, I can see that they are all acceptable with no stars included. Having reviewed all of the samples, we can now execute the process with the green tick. This will generate a background image and a new integrated image with a DBE label affixed to it. The first thing to do is to have a look at the background model to see the sort of gradients that have been picked up. And in order to do this, you need to apply an automatic screen stretch. With this button. Here you can see that the gradient that has been subtracted from this image is very large. It's not particularly bright. I think the conditions that I shoot under, I mean, I don't get a huge amount of gradients, but if you're in an area with a lot of light pollution, you will get more dramatic gradients. So there we have the gradient picked up, and that has been subtracted from the image. Here's the new image, and that is the integrated image that's now had the gradient removed from it. And that is how the process works. To cancel it out, use the red cross at the bottom. There are cases when using a one-shot colour camera when you have very bad light pollution, and this can affect each of the red, green and blue channels differently, and it may be difficult for one application of DBE to the colour image to actually pick up all of the gradients. In this case, I'm going to show you how to split the one-shot colour image into separate RGB images, and then DBE can be applied to each one. The first thing to do is you need to apply the RGB working space process to the color image with the settings shown, and you need to apply an equal luminance coefficient of 1 to each of the color channels. This is shown in the top right image. This won't affect your chrominance at all, so don't be concerned. The process can be found under Process, Color Spaces, RGB Working Space. Once that process has been applied, you then use channel extraction to separate the red, green and blue channels. Use the settings shown opposite. So drag the blue triangle to your one-shot color integrated image, and it will split it into 3 images, one red, one green, one blue. The process can be found under Process, Color Spaces, Channel Extraction. You now apply dynamic background extraction, as I've previously described, to each separate red, green and blue channel images created. Once you've done this, you then want to combine your three images back into a single color image, and to do this you use channel combination. This is found under Process, Color Spaces, Channel Combination. In each of the red, green and blue boxes you enter the relevant red, green and blue image titles, or you can show them from a view by clicking on the little box on the left hand side. It's fairly simple to do. Once you've recombined them, you're back to a single RGB color image, but you've managed to extract the gradients from each of them separately, and it should be a great improvement. The final section of this tutorial will look at linear noise reduction, and for this we're going to use multiscale linear transform. It's very important that you carry out some noise reduction at this stage, because what you want to get rid of is the high frequency noise which tends to sit in the background. If this noise isn't removed at this stage, then it will be amplified by future processes, such as when you stretch the image to make it non-linear, and then if you do any curves transformations to increase the brightness of the image. So it's a good idea to get rid of it at the linear stage before you accentuate it. The process uses wavelets to break the image into separate scales. To get rid of the high frequency noise, which tends to sit in the much smaller scales, you apply the process more aggressively at these scales. Again, it's a dynamic process with interaction, and there is a built-in mask. In this image you can see the high frequency noise that I'm talking about. It tends to look like a pixelated pattern. With a one-shot color camera, it'll basically look like looking into a jar of hundreds and thousands. You can also see that there is, as expected, less noise in areas with a higher signal. So this is the edge of a nebula, and there's far less noise. Therefore, in order to not destroy any detail, we don't want to apply the noise reduction to the areas with good signal and with detail. The process is found under Process, Noise Reduction, Multiscale Linear Transform. Here we have the process window. The first thing we do is change from Starlet Transform to Multiscale Linear Transform. We want 5 wavelet scales. This works for the majority of images, and also we want to generate a linear mask to protect the areas of high signal. We're able to evaluate the mask and preview it, and for this we use the dynamic preview window button, which is the third one along from the left hand side. You can see now I'm moving the amplification slider so that I can tune the mask to cover the areas of high signal. Also, I use the smoothness slider so we don't end up with any very sharp edges between areas of signal and areas without signal. That mask is acceptable, so I unclick the review mask and we go back to the preview of the galaxy. So now I'm going to apply noise reduction, again to small scales. So I'm going to apply 5.5, around 90%, and then I'll gradually move down, and you can see that I'm reducing the amount of noise reduction as the scales increase. When we get to the large scale of 16 pixels, it'll be a very small amount of noise reduction. The other great thing about this process is you may be able to see in the top right corner of the preview screen that as I move the sliders, the preview window is doing the calculation on the image. So it really becomes a live view of what you're doing, which is very useful. So there we've done the 5th scale and a very small amount of noise reduction. The other thing we can do is click this button and we can zoom in to see the effect that it's having. Choose an area with, obviously with background and then with some signal, and you can see that we've got a much smoother background, but the areas of higher signal have not really been affected and the detail is still there. If we want to increase the noise reduction a little bit more to the background, you can go in and move that slider along. So I've gone up to 6.5, 7. The preview window calculates the change. Again, change the 2nd scale, slightly more aggressive. This is just to demonstrate what you're able to do with the live view. Once we're happy, we hit the blue box, apply, and the process takes place. Close the preview window, close the process, and then you have your noise reduced image. Zoom in, again, have a look at the area where you've tried to do the noise reduction, and you can see there's been an improvement. You're not going to get rid of all the noise, that won't happen at this stage. In this image you can see the result of the noise reduction, and I think you'll agree there's a very good improvement in the high frequency noise of the background areas, and there hasn't been any diminution of the detail. And that completes this second tutorial. I hope you found it useful.